Welcome to another video by Only Keypads. In this presentation I will be demonstrating the protocol of the UART data line sending data from the PIC12F675 to the Tera Term emulator software. I will also show the basic circuitry that's involved and the basic code that's required for the PIC12F675. So stay tuned. I believe you're going to find this very interesting. This presentation is going to demonstrate how to communicate with a UART connection between a PIC microcontroller and a PC running the Tera Term emulator software. I'm only going to be using the TX data line for this demonstration, and the PIC I'm using is 12F675. Coming off the PIC, I just have an LED that flashes to let me know that the PIC is up and running. Then of course I have the TX data line connected to a FT232RL serial to USB converter adapter modular, and that has a USB cable coming off it that goes to the USB port on my computer. The RX line I have connected, but it's not going to be used in this demonstration. I have two 1K pull down resistors, one on the RX line, one on the TX line. I have a PIC12F675 connected to the 12F675. You could use a PIC12F675. Okay, it doesn't have to be a 3. And then I just show some pinouts here, okay, of the PIC12F675 and the microcontroller. Okay, so with that, I'm going to go into the MPLabX IDE, and the first thing you'll want to do is create a new project. So microchip embedded is selected. You want to do a standalone project and just click next. Okay. Now we got to select the PIC that I'm using. Okay, we're going to be using, I'm using somewhere in the mid-range PIC, and it'll be the PIC12F675. Get down here to it. You can also just type it in, which is probably easier. There's 12F675. There it is right there. Just double click it. That's the PIC12F675. I'm not using any tools right now in the MP Lab. I'm not using no simulator, so we'll just leave no tools. Okay, just click next again. Just leave none. Okay, and go next again. The compiler will be the Ascii compiler, and click next again. The project name, we'll just make it something, we'll just call it a shell project. Alright, we'll just do that. Alright, we'll just do this shell and then project. Alright. Okay. And it's going to be saved. I already have this set up. It's saved in my documents. I have an MP Lab projects folder. Okay, you can browse and put it in whatever folder you want to put it in. Okay, and I have it set as the main project for now, and we'll click finish on that. Okay. Alright. Okay, so it's over here right now. Alright, so we want to go to source file. Okay, highlight the source file. Okay, left click on it. Okay, and we want to go new, and you want to go main C. Okay, just click main C. Now we got to give it a file name. Okay, so we're going to call it the same as what we did on the project folder. Make it simple. We'll just say show. Alright, and underscore, and we'll do project again. Alright, CT. Okay, and that's it here. Okay, and then you just click finish again. Okay, and we'll wait here a couple seconds. Okay, here we have it right here. Okay, alright, and this information here, this would be a starter where you want to put some code in, but what I want to do is I have the C code already in a text file. Okay, so I'm just going to copy and paste that in. Okay, I'll be going over this code a little bit later on, so let's just edit, let's select all. Alright, and that's all the code selected. Okay, all the way up to here. Alright, and we're just going to copy it. Alright, and we'll just get rid of that, we'll minimize that. And we're just going to get here, we're going to insert it right in here, left click and paste. Okay, alright, and that inserted all the code, okay, into this project that I'm going to be demonstrating. Okay, alright, so the next part of the videos is going to be going more a little bit explanation into the UART, and then it'll be into demonstrating the code actually communicating with the PC running the Tera Term emulator software. Okay, so there's going to be some multiple parts to this presentation. Okay, so with that, I'll get ready to move on to the next part of the video. In this video, I want to explain the basic diagram of the UART TX data transfer before getting into the actual explanation of the code for the PIC microcontroller. And I built a basic diagram here showing the data bits that will be transferred from the PIC microcontroller through the data wire down to the PC running the Tera Term emulator software. And I did a little bit of write-up here, and I'm just going to use that as a guide. Okay, so it can always be referred back to. Okay, the transmitter, which is this part of the diagram here, this is be generated by the PIC microcontroller. It holds the data wire high, indicating a standby mode, so the receiver is idle. So in other words, the PIC microcontroller will hold this data line high, and that basically is indicating a standby mode, and it puts the emulator into a idle mode. In other words, it's not expecting any data transfers, it's just sitting there waiting. Okay, now when the transmitter pulls the data wire low, it indicates a start of the data transfer to the receiver. So you can see here at the falling edge of this high, okay, as soon as the emulator sees that falling edge, okay, it's getting ready for a data transfer, and I stated that here. The falling edge of the data wire alerts the receiver to sample the data line for a valid start low state. Okay, so as soon as the emulator sees the falling edge, it goes and it samples the line. Okay, now if you notice, the receiver clock pulse samples the bit at an average point in time along the length of the data pulse, not too close to the rising or falling edge of the data pulse. It's basically around the middle. So you see how the data pulse, it didn't sample right at the falling edge. It samples somewhere in the middle of this data bit. Okay, and the reason that occurs is so no false data is received. So when this method's used, the data is considered a valid set of a valid bit by the emulator. Okay, so once the start bit is verified by the receiver, the clock samples the data wire at the selected baud rate, and based on receiver configuration, that 8 data bits will be sent along with 1 stop bit. So when the Tera Term is configured, it's configured for one start bit, 8 data bits, and one stop bit. So when the emulator sees the start of a data transfer, it knows that it's going to be receiving 8 data bits, and then it's going to receive one stop bit, and it'll know that that's the end of the data transfer. Okay. Sometimes I guess there's emulators can be set up for more bits, maybe 10 bits, so forth and so on. Okay, then it would expect that many bits, but for this presentation it's expecting 8 bits and then one stop bit. Okay. Alright, so at this time, you don't want to overthink how this emulator generates these clock pulses and so forth and so on, because there's numerous articles on this, and this presentation is just to transfer data to the emulator, which is the receiver. Okay, so if there's going to be a receiver involved with the PIC microcontroller, that's going to be for a whole nother presentation. Okay. Alright, I'm going to go down here a little bit. Okay. Alright. Okay, so the following is a guide used to hard code the PIC in simple terms. In other words, this software that I put together is very basic, okay, but it works. Okay. Okay, and I'm just stated here, numerous UART resources refer to the TX data transfer clocking at the same baud rate as the receiver clock. So in other words, some articles, are going to say that this clock here relates to the clock here. They have to be at the same baud rate. Okay. But, this is relevant, and not to be disputed, but the TX and RX clocks are not synchronized to one another, so they run at independent of each other. See, these are not synchronized clocks. Okay, so that's why it says universal asynchronous receiver transmitter, UART. Okay, and basically this makes it one of the easiest or easier protocols to design. I'm not going to say the easiest, but one of the easier ones. Okay, and this code is designed to simplify the TX transfer without designing a TX internal clock in the code. In other words, my clock, or my timing here, is not an actual clock in the code. Okay, it's going to be built on a delay type timer. That's how I built the code. Okay, so when with the receiver set for 2400 baud, okay, that's the receiver here, that's set at 2400 baud. Okay, this equates to 1 divided by 2400, or 0.416 milliseconds per bit, or 416 microseconds. Okay, meaning the receiver clocks the data at every bit. Okay, based on the 2400 baud at 0.416 milliseconds, or 2400 bits per second. Okay. Alright, like I said, this stated here, this works in theory. Okay. Okay, but it's close enough for the programming of the PIC duration timer. Basically, in the code, it's going to be a delay timer. Okay. And I'm going to finish here by saying the PIC duration delay timer will be initially set for 0.416 milliseconds, and it's going to require some tweaking because the PIC, it has instruction execution times and other peripherals it has to deal with, so the timing isn't always perfect when it comes to executing a delay. Okay, and because the receiver clock expects the next data bit to be valid and has no way to synchronize with the PIC delay. Okay, this 0.416 milliseconds will have to be offset in the PIC code. Okay, because you have to find a happy medium, because this clock pulse from the receiver is going to sample somewhere in the middle of this data bit. Okay, so there's going to be a little bit of an offset to this delay here. Okay, but then from research I found is that the TX and RX timing can be within 10% of each other. Okay, so there's going to be room for error in this. Alright, okay, and with this going to move on to the code. In this video I just want to give a brief explanation of the code that I wrote for the PIC12F675. It's written for the UART TX transfer of data from the PIC to the Tera Term emulator. I'm not going to get much into the programming parameters for the PIC, okay, but these are the parameters that are set up. My clock frequency of the PIC. I defined some variables here, okay. I defined a UART RX pin on the PIC as GP4. I'll bring that up here in a second here. Where's I at? Okay. All right, I'm going to bring the PIC up here. Okay, so the UART RX, which is not being used in this demonstration, is tied to pin GP4, which is pin 3 on the PIC. The TX line, which is being used, is tied to GP2, which is pin 5 on the PIC. That's going to be the data line for TX. That's the data line going out of the PIC. I have an LED on GP5 just flashing to let me know that my PIC is up and running. That's basically all that does. Okay, so I'm not using a lot on the PIC. Okay, and it's only an 8-pin device anyhow, but that's all I require for now. There's some variables I said here. There's a integer key Ascii. I have it a fixed hex value of 0x47. Eventually that's going to be the Ascii value that's going to be coming from the keypad into the PIC microcontroller. And then this other variable here, this key TX, all I'm going to be doing is transferring this hex value to this variable, because my programming down the road may require that I don't want to change this key Ascii value at a certain point in time while maybe another key is coming in. Okay, so I want to just transfer this into here. Okay, and then at that point in time, then I'll make the other. Then I'll transfer from the key Ascii to the key TX. Okay, you'll see how that works when we get down here a little bit further. Okay. All right, and then what I do next is this is just some more configuration of the PIC. This is the analog selects. I'm setting all my ports as digital ports. So all of these ports are GP0 through GP5 is all set for digital. I'm not using any analog. Okay, that's all that's doing. There's some things turned off here, the converters and comparators and stuff. I'm not using any of that. The tri-state I/O, I have a hex value of 0x18 plugged into that. Okay, that sets GP2 as an output. Okay, I'm going to get up here a little bit. Okay, here we go. Okay, GP2 is actually the TX data line, so that has to be an output because we're transferring data from the PIC to the Tera Term emulator. Okay, GP3 is an input. I'm not using that in here anywhere. GP4 is an input. If I was using the RX data line, that has to be an input because that would be where the PIC would be receiving data. Okay, and then GP5 is the output for my LED. Okay, so that's all that tri-state I/O is doing there. Okay. Okay, then on this next line is where I'm setting the UARTX line high. Okay, that's this TX line. I'm setting GP2 high. Okay, which is the data line, the TX data line. That's going to be set high going out. Okay, and if you recall back, get this diagram up here. Okay, the data line is set high to indicate a standby mode. Okay, so the receiver is going to sit idle here, okay, because the line is constantly high. Okay, so it's not going to be looking to receive any data at this point. It's just going to sit here idle. Okay, and that's what this line of code does here. Okay, this UARTX is set high. Okay, it puts the data line in standby. Okay, I noted it here, and that's all that's doing right now. Okay, all right. Okay, so then this here is the routine that blinks my LED. Okay, lets me know that the PIC is up and running. It's just a visual indication. Okay, and every time when it ends this, when it goes through this loop at the end here, okay, it's going to take that key Ascii value and put it into the key TX value. Okay, remember up here I declared these two here, key Ascii and key TX. So that's all that's doing, taking this value, this 0x47, moving it into the key TX. Okay, and then after that I'm going to run this function, this send data. This is where it's going to jump to the routine to send data to the UART. Okay, it's going to send data out on the TX line. Okay, so it's going to jump from here, it's going to jump down to here, it's going to jump to this function. Okay, now when it does that, it's going to set the UARTX line low. Okay, it's going to set that when I get back up here. Alright, it's going to set GP2 low. Okay, and if you recall back, okay, let me get back here. You recall back on the falling edge here, it sets a low bit, and that indicates a start. Okay, so the receiver will read that, will see the line go low, and it knows that it's getting ready for a start of a data transfer. Okay, we went through that before on the other video. Okay, but that's what that line's doing. It's creating this falling edge here. Okay, alright, then after that it would jump down. Okay, but it holds it for so long. I want to point that out. This is where it jumps to a clock routine, because I have to hold this line. Let me get back here. I don't want to complicate this too much, but I have to hold this start bit for a certain period of time so this clock pulse from the receiver has time to actually read it as a valid bit. Okay, and that's where it runs this clock routine then. So it jumps from setting the line low down to this clock function, and that's at the very end of the code down here. Okay, and that's just a basic delay loop. It delays that line, holds it low for 0.516 milliseconds, because remember 2400 baud was 0.416 milliseconds per bit. Okay, I had to offset this a little bit, okay, for it to work properly. Maybe it's something to do with the instruction timing here and so forth and so on, but I had to kind of put an offset in here to hold that bit just a little bit longer for the receiver to read it as a valid data bit. Okay, so that's all this delay is doing here. That's all this subroutine does here, is one line of code for the clock. Okay, and I'm calling it a clock, and it's just basically a delay. It's not actually clocking all the time. Okay, like you would expect a clock to do. Alright, so after that, then it jumps here. Okay, then it says if the key TX, okay, which is the ASCII value of the key that was pressed, okay, it ends with a 1, okay, but this is where it might get a little bit confusing. This is a shift, to shift the data bits, okay, on this key TX hex value. Okay, I want to jump to another thing here, right here. Okay, on the UARTs will read the data bit from the least significant bit to the most significant bit. Okay, so that hex value from that key, let's say it's the letter M. Okay, that's going to be 4D in hex. So hex 4D in binary is 0, 1, you can see it's 001101. Well, this 1 is the least significant bit. So we want to read this bit first, and we want to transmit this bit first down to the receiver. Okay? So that's what this does here. Okay? That shift 0 means we're not shifting this, we're just reading this very first bit. Okay? And that's what this is doing here. Okay? And if it ANDs with a 1, okay, a 1 and a 1 is a 1, okay, it's going to go here. If key X AND it with a 1 is a 1, it's going to set the UARTX line, the data line, high. Okay, because remember the TX data line was up here. Okay, that went out on GP2, UARTX. It's going to set GP2 high. Okay, alright, or if that bit, that least significant bit, is low, it's going to say else. It's going to set the UARTX line low. So we'll set the line low, indicating a 0. Okay, the bit's low. Okay, so either it's high or it's low. Okay, so if the first rightmost bit is a high, it's going to set the UARTX line high. If it's a low, a 0, it's going to set the UARTX line low. Okay, and then it's going to jump back down to that clock routine, because we have to hold the line at that state for the clock to read it. So we're just going to jump down here. We're going to put that delay in effect here. Okay, and then that's going to hold the line. I get to my other thing here. Hang on a second. Okay, this will be that first bit that we're reading. Okay, so it has to hold the line for that certain amount of time again for this second clock pulse to read it. Okay, I think you can start getting the idea here what's going to happen. Okay, once it jumps out of that clock routine, then it's going to jump to this if. It's going to say if that key TX hex value, we're going to AND it with a 1 again, but now we're going to shift 1 bit to the left. Okay, we're gonna read that bit in this line of code right here. Okay, which means if this bit here, it's going to read this bit now, the second bit from the right, which is this bit here. Okay, it's going to read it, either it's going to be a 1 or a 0. Okay, and if it's a 1, it's going to set the data line high. If it's a 0, it's going to set the data line 0 and run the clock again for the receiver to read it. I think you can start seeing, I don't have to go through all these, I think you see what's going to happen here. First we don't shift, we read the rightmost first bit, then we shift 1, we read the second. Okay, then we shift 2. Okay, we just keep on shifting to the left. We read 3, 4, 5. This is the same loop, the same thing. Okay, 6, 7. This is all 8 bits, 0 through 7. Okay, so the receiver read all 8 bits, 0 through 7. Okay, then when it's done reading them, after this last clock down here, we have to send out a stop bit. And that's when we make the UARTX line high, because the receiver reads a high to end the transmission. Okay, so when it reads that high, it knows that that's it. There's no more data to be sent. It goes back in idle mode. It sets the line high. Okay, so it also sets the data line, what we said before, in standby. Remember back here? As long as this line is high, it's considered standby mode. Okay, so the data line's high, and this keeps the receiver in idle. Okay, it's going to wait for that falling edge again to start receiving data. Okay, and the routine just keeps on going round and around. That's all it does. This is very basic. Okay, this is just for somebody that wants to get started in putting their own UART code together. Okay, I'm just going to use, the reason I put this together is because I want to use a basic PIC controller, and the ones I'm using don't have any serial ports on them, and I just want to read what key is pressed on my keypad, you know, with what letter it is or what number it is, and I want to get a visual on an emulator. So that's the reason I put this together. I'm going to insert this into some of my other code, okay, on the encoders for the keypads for my purpose only. Okay, but that's pretty much it. On the next video, I'm going to demonstrate this actually working and sending characters to the Tera Term emulator. Okay. All right. So I'll catch you on the next video. Okay. Up to this point in this presentation, the basic UART data transfer was explained. The code to do the data transfer was explained, and how to build the project and copy the code into that project was explained. Now the next step is to actually demonstrate the code and that it actually works. Okay. So right now, in this key Ascii variable, there's a 0x47 hex in there. Okay, and that 0x47 on the Ascii table is actually the uppercase G right here. Okay, this is the hex column, and 47 is uppercase G. Okay. All right. So what I'm going to do now is I'm just going to minimize this, and I'm going to launch the Tera Term. Let me get this out of the way. And we're going to launch the Tera Term emulator. Okay, so you want to select serial, the COM port that your project is connected to, and I'm on COM 3, and we're going to OK that. Okay, now we're just printing a bunch of garbage out here, you can see, because the baud rate isn't set right. Okay, so I got to go down to serial. See the baud set at 9600. In our project it's set at what, 2400. There's 8 data bits, no parity, and 1 stop bit. We went through this before when I explained the UART protocol. Okay. All right, and I'm just going to click 2400 baud, and that's going to be click new setting, and there we're printing the uppercase G. Okay, I'll just clear the screen here. Where we at? There we are. Clear screen. Okay. All right, we're printing uppercase G, and like I said, that code just keeps on looping and, you know, printing the G. Okay, this is for demonstration purposes. So I'll minimize that right now. Okay. And now back here, we're going to change this here. Okay, let's go to something else. Let me bring up the Ascii table here real quick. Right here. Okay. All right. Let's make it a number. Okay. Let's make it a number 7. Number 7 is a hex 37. Okay. So let's change this to a 37. Okay. So we'll just go here. We'll change this to 37. All right. And we're going to save it. And we're going to compile it. Okay. That'll be done in a second. Okay, I'm going to minimize this out. Okay, now I'm going to connect my PIC. I'm still connected to the PIC2, so I'm going to plug the PIC2 in to my USB port here. Okay, let me get that plugged in. Okay. All right, and that's going to be the PIC Easy. I'll launch that. Okay, I'm connected to the PIC2. I'm going to browse for that hex file. Okay, it's under Documents, MPLabX Projects. Okay, and I'm using this project here. I demonstrated pasting the code in this shell project, but I'm using this. It's the same code. Okay, and we go to this default production, and there's the hex, and we'll open that up, placed it in there. I got to find my PIC controller. It's going to be the mid-range standard 12F675 right here. Okay, alright, and we'll see if it writes down to it. And it's running and it's writing down. This is good stuff. I like it. Okay, now let's go over here to the Tera Term emulator. Yep, see what it's printing. Alright, some reason it's not printing the 7. Alright, let's see what's going on here. Something ain't right. Oh, no, wait, I am in show project. I'm sorry. Okay, so that's fine. This is a demonstration. So let's go here to browse. Okay, now let's go back to documents, MPLab projects. Let's go to show projects. That's where we pasted the code in. Okay, and we'll go production again. But I'm going to have to change that. Hang on one second. Okay. Alright, this is what it's all about. So let's go show projects. We'll get rid of this right now. Okay, we did build that. Okay, so we're good. Okay, I just want to double check that. Okay. Alright, so let's go browse again and make sure I'm in the right one here. MPL projects, show projects. Okay, distributed, default, production, hex file, open it. Okay, now let's write that one down. Okay. Okay, let's see what we got now. There, we're printing the number 7. Okay. All right. So I just wanted to demonstrate that this all works. Let me clear the screen here. Okay. See, we're printing 7. All right. So let's just run another real quick one here. Okay. What do you say we print some type of character? Okay. Alright, I'm sure everybody sees what's going on here, but while we're demonstrating, okay, let's print let's print the hashtag. The hashtag is hex 23. Okay, so we'll change this guy here to 23. Alright, back this off. We'll go 23. Okay, and we'll save it. And we'll build the project. There it goes. Okay. This MPLab X, it takes a lot of resources. I'm running 8 gig of RAM on this computer right now, and it's running fairly fast, but it has a lot of overhead to it. Okay. Alright, so we want to go here now, and this should all be the same, and we just have to write to it. Okay. There we go. And we're printing hashtags. Alright, so it works. Okay. So this is a nice little project here. There's all the hashtags. Okay, it just keeps on running the loop. Like I said, this project here, this UART, is very simple, but all I'm using it for is to when I press a key on my keypad, I want to show on my computer. Okay, so I get actual visual that things are working, and this can be expanded on. I mean, you can modify this if you want to print some string data out. Okay, you have to build some type of a loop for this key TX hex value. Okay, that after it prints the first character, then it will come and it will reload that key TX with a different character, and then it'll run this loop again and print that character, and so forth and so on. Okay. Alright, so it's a nice little handy tool, and it's something to mess with, and it's very basic. There's no real high level complicated code here. Okay, so just a hobbyist that wants to experiment a little bit with some UART, I really hope this helps out. Okay. Alright, I want to thank you for watching, and I hope it becomes useful. showing where to go and get the code for this project. In your browser, just type in onlykeypads.info and you should come right to this site. Go to PIC projects folder here. Go to the PIC12F675 UART. Scroll down. This is the link for the text file that contains that PIC code. Just click on that. Okay. And here you can view the code, or you can download it, or you can print it. There's also going to be an Instructables project that contains a more detailed description of the build, and that's going to be coming soon. Okay, so I hope this helps some hobbyists out there. Okay, and thanks for watching.